Let's start share screen, the usual routine. Hopefully this will work quickly. Okay, here we are. I don't have very much review tonight, but there's only a minute left, so let me get started on it. So this is my review page here. We're just got started on central force motion in the last lecture. Let me just go over some of the main points. In central force motion, you've got some object that produces the force field, and if you put it at the origin of your coordinates, then that sort of sets up the problem. However, if the mass of the object is not very large, then the frame which is attached to it is not an inertial frame. So initially, we'll make the idealization that the mass of the object producing the force field goes to infinity, or at least is very much larger than the mass of the object that's in orbit. And if you do that, then you get a single body Hamiltonian, single body problem, because in that case, then the object is producing the force field is not moving. So it doesn't have any dynamics of its own, and all the dynamics is connected with the orbiting particle. And if so, you get a one body problem in which the Hamiltonian is the kinetic plus potential energy for that orbiting particle. Now, in fact, a large mass for the force producing object is sometimes a good approximation. I mean, for example, in the solar system, the sun is about 1,000 times as massive as Jupiter, which is the biggest planet. And in a hydrogen atom, the proton is about 2,000 times more massive than the electron. And the ratio is even larger for heavier atoms. So sometimes this is a pretty good approximation. In any case, in this discussion of central force motion, we'll start with the idealization that the mass capital M goes to infinity, so that we have this single one body problem. Now, I didn't have too much time on this in the last lecture at the end, but the main points is that this Hamiltonian commutes with the rotation operators. The rotation operators themselves are defined this way. We went through that in a previous lecture. Here's the action of rotation operator on a wave function. Bring it back here. And from this, it follows that the Hamiltonian commutes with the rotations. The logic here is that the Hamiltonian is a function of dot products of vectors, momentum p dot p and r dot r, or x dot x, position vector. Dot products are invariant under rotations. The details of that logic is something we'll fill in a later lecture, but for right now, that's the basic idea of it. Now, if H conjugated by U reproduces H, so we say the Hamiltonian is invariant under rotations, it's equivalent to saying that the Hamiltonian commutes the rotations, because I could multiply through from the right by U, and that would clear the U dagger here and give you UH is equal to HU is what it would give you, or the commutator is 0. Now, if H commutes with all rotations, it commutes in particular with infinitesimal rotations, and therefore with orbital angular momentum, which by definition is the generator of those rotations. Conversely, if it commutes with all three components of L, it commutes with any function of L, which includes the rotation operators and other things too, for example, L squared and LZ. So these implications work in both directions here. In any case, we end up with a conclusion that H, L squared, and LZ is a set of commuting operators. And so we'd like to find simultaneous eigenstates of all three of those. Now, the eigenstates of L squared and LZ are what we've been calling the standard angular momentum basis. And we worked through that in a previous lecture, I think the last lecture, and found that the eigenfunctions of L squared and LZ in this situation of a single particle moving in 3D space, those eigenfunctions have the form of an arbitrary radial wave function, which I'll call capital R of lowercase r times a YLM. And because of the arbitrariness of capital R, that means that these wave functions are degenerate, and that the L squared and LZ by themselves don't form a complete set. Question then arises is that if we add the Hamiltonian to it, do we get a complete set? And the answer is yes, and I'll show you how that works out. It means that the simultaneous eigenstates of all three observables are non-degenerate. In any case, that I think summarizes where we ended up last time. And the next step then is to try to find the radial wave function by demanding that psi be an eigenfunction of not only L squared and LZ, but also the Hamiltonian H. So that's the setup. And let me then proceed to the actual meat of the lecture, then the content of the lecture.
Hi, can I ask a question?
Yeah, sure. you want me to put the page back that I just had? Hi, was there a question? There was a question, but I think it got lost. Is there a technical difficulty?
Oh, hello. Can you hear me now?
Yeah, yeah.
Okay, sorry. I think my internet is a little bit unstable.
Oh, that's
Sorry, could
okay.
you just remind me the top right where you write u of r psi of x and then
Yep,
equals
yep,
psi.
yep.
Um, sorry, where did that come from again? What does
Well,
that say?
that came from I think the last lecture where we worked out the action of rotations on wave functions in 3D. And there's a set of notes on that. It has to do with spherical harmonics and things like that. So one of the things we found is that this is a logical definition of rotation operators on wave functions in 3D,
Right,
as explained in those notes. And if you make this definition, then the generators of those rotations are the orbital angular momentum, which is defined as r cross p or x cross p. And
right,
the
right,
and the standard angular momentum basis is as I quote here. It's the YLMs are the essence of it, but there's a radial wave function too.
right. Okay, I remember
Does
now.
that help?
Yeah, thank you.
Okay, good. All right. So what we need to do then is to take that form, the eigenfunction of L squared and LZ, and just plug it into the Schrodinger equation. For that, we need to worry about the kinetic energy operator, it's p squared over 2m. Of course, there's a differential operator that's minus h bar squared over 2m times the Laplacian. So if I write out the wave equation for the Schrodinger equation for the Hamiltonian now, you can write it this way: by converting the Laplacian into spherical coordinates. Here's what you get: you get minus h bar squared over 2m, and then you get 1 over r squared, and then partial respect to r, and then r squared times another partial respect to r, and then you get an operator which is L squared over 2m r squared, and that is the kinetic energy p squared over 2m. So that acts on our wave function, which is r of r times y lm of theta and phi. And then we add to this the potential energy, which depends only on r because that's what you mean by a central force problem, times the wave function, which I'll copy again, the form that we have for it. And that's equal to the total energy E times the wave function r of r times y lm of theta and phi. Now the hard part of this, of course, is the kinetic energy here. And you can get the convert the Laplacian to spherical coordinates by a calculation that takes several pages to do it, or you can look it up if you're not motivated to do that. And if you do, you find there's radial derivatives and angular derivatives, and the radial derivatives I've reproduced here. The angular derivatives can be organized into the form of L squared over 2mr squared. That requires to have a formula for what the operator L squared is. Well, the L is the angular momentum, and its components are differential operators because they're r cross p, the components of that, xpy minus ypx. And you need to convert those into spherical coordinates, so they have angular and radial parts. And I discussed that in the last lecture. So you assemble those pieces, and you'll find that L squared then captures the angular part of the Laplacian operator. So there's some algebra in setting that up, but it's straightforward to go through it. I won't do that. I won't go through it. But what I will do is I'll say some things about the classical mechanics of this kinetic energy. So if we do the classical mechanics, the kinetic energy p squared over 2m can be written this way. It can be written as the radial momentum squared, pr squared over 2m, plus, as it turns out, L squared over 2mr squared. That's a classical calculation. The piece of r is the same thing as m times r dot classically. So this first term here is the same thing as m times r dot squared over 2. And you can see that this, therefore, is the kinetic energy in the radial direction. To make a classical picture, let me just draw this in the xy plane. Of course, it's really in 3D, but if we just put it in the xy plane to give you an idea of what's going on, if I have the position of the particle as position vector r like this, and a velocity which is pointing out like this for some motion, we can take that velocity and we can project it in two directions. One is in the radial direction. That's the radial component of the velocity. And the other is in the angular direction. That's the angular component. Now the radial component has a magnitude of just simply r dot of the velocity. And the angular part has a component of r theta dot, where theta is this angle here, of the position vector r. So that's just simple classical mechanics. So if you multiply by the mass here, you get this radial momentum PR. PR comes from mr dot and so on. And so what this shows you is that the total kinetic energy then has got a radial part and an angular part. This is the radial part, and therefore that must be the angular part. Well, in fact, it is, because the angular momentum L is equal to m times r squared times theta dot. And if you compute L squared over 2m r squared, what that turns into is m over 2 times r squared theta dot squared, which is just the 1/2 mv squared of the angular part. So classically, this formula then just breaks up the kinetic energy into its radial part and its angular part. And in quantum mechanics, that's the same thing. This first operator here, this complicated operator involving radial derivatives, is physically the operator that represents the radial part of the kinetic energy. And this part is the angular part. Okay, so this classical digression was just a way of giving a physical interpretation of these terms that occur in the Schrodinger equation. Now the L squared operator, which appears here, is acting on this wave function, which is an eigenstate of L squared, because that's how we set it up. There was a standard angular momentum basis. So it acts on eigenstates of itself and just gets converted into its eigenvalues, which is L times L plus 1 times h bar squared. And if we do that, then you see that then there are no more angular dependence anywhere, neither derivatives nor functions of angles in the operators that are acting on the wave functions here. And that means that we can cancel out, let me cancel things with red ink. That means we can cancel out the YLMs because it's a common factor now in all three terms like that. And if we do so, we end up with an equation just in the radial variable alone. And let me copy down here what that is. It turns into this. It turns into minus h bar squared over 2m, 1 over r squared ddr times r squared times d of capital R with respect to lowercase r. Capital R is the radial wave function, lowercase r is the radial variable. This is then added to we have the centrifugal potential. Let me write it this way, plus u of r times r of r is equal to the total energy times r of r, where u of r is the sum of the centrifugal potential, of this L squared term, which turns out to be the centrifugal potential, L times L plus 1, I haven't mentioned that yet, but that's what it is, over 2m r squared, plus the second term coming from the total potential, V, like this. So we combine this factor in with the potential. We call this the effective potential, U. We call this part the centrifugal potential. And we call this part the true potential, because that's what it is. And it's the effective potential which appears in this what we call radial Schrodinger equation appears here. In fact, I'm going to call this version 1 of the radial Schrodinger equation. I'll give you version 2 in just a minute. But I want to comment here because the centrifugal potential, as I just explained, physically is actually a part of the kinetic energy. It's actually the angular part of the kinetic energy. But given conservation of angular momentum, it appears as a function of r, although it's parameterized by L, the angular momentum quantum number. So in other words, it looks like a potential. And so mathematically, we throw it in with the true potential to create an effective potential U of r, and that's what appears in this radial Schrodinger equation. So this is what the equation we need to solve to find the radial wave function r of r with a given energy E. I'll say more about that in a minute. But before I do, I want to tell you about version 2 of the radial Schrodinger equation. Version 2 is obtained by making a substitution, f of r, a new radial wave function, is equal to r times capital R of r. It's just the old wave function scaled by factor of the radius. And if you plug that into the version 1 of the radial Schrodinger equation and grind through the algebra, here's what you get. Is you get minus h bar squared over 2m times f of r double prime plus u of r times f of r is equal to E times f of r. Let me box that too, because I'll call this version 2 of the radial Schrodinger equation. It's just based on this simple formula, the simple transformation of the radial variables, the radial wave function, as you see above. So I'll use capital R for version 1 and lowercase f for version 2, different notations and used in different books. The notable thing about version 2 of the radial Schrodinger equation is that it looks just like the one-dimensional Schrodinger equation where you have a variable x that just runs along the x-axis, except for a couple of small differences. One of them is that the variable r only goes from 0 to infinity, whereas x usually goes from minus infinity to plus infinity. And also in the 1D Schrodinger equation, you'd have the true potential here, whereas in the version 2 of the radial Schrodinger equation, you have the effective potential, which is the sum of the true potential and the centrifugal potential. But except for that, it has the same form, and it makes it easy to remember it's easier to remember version 2 than it is version 1, because it just looks like the usual 1D Schrodinger equation. All right, you can solve either one of these Schrodinger equations, whichever one is easier for the problem you've got, and then transformation of the radial wave functions is easy. Okay. Now then, it turns out that the eigenfunctions of either one of these two radial Schrodinger equations are always non-degenerate. I'll explain that in piecemeal as I go along here. But one of the things that means is, if I go back to the review page that I introduced earlier, it means that if the simultaneous eigenfunctions of all three of these observables are non-degenerate, it means that they form not only a commuting set, but actually a complete set of commuting observables.
Sorry, I just have a question if I could ask. I feel like in the notes in one dimension, you said that, so in one dimension, eigenfunctions are always non-degenerate. Is there a sort of a parallel here? I know we're not in one dimension, but we have a sort of.
Actually, no, I'll get to that. And actually in one dimension, it's not true that they're always non-degenerate. The condition, I'll get to this in a minute. The condition is that if the wave function is forced to vanish at some point on the x-axis, which usually happens because of boundary conditions like a hard wall or something, including, by the way, the point at infinity, if that's the case, then the wave function is non-degenerate. That's how it is for a 1D problem. But it doesn't apply to all 1D. For example, the free particle, it doesn't apply because the wave function is not forced to vanish everywhere. And for a free particle in 1D, there's actually two linearly independent solutions, either the IKX and either the minus IKX, that have the same energy. Okay, so I'll get back to that in a moment. But I'm jumping ahead a little bit because I haven't explained why. But it turns out that in this radial wave equation, it turns out the solutions always are in fact non-degenerate, and that means that, as I was saying a moment ago, that HL squared and LZ actually form a complete set of commuting observables. So we'll get back to that in just a moment, but I'm going to build up to it. All right. Now I want to say something about quantum numbers. These two radial wave equations are parameterized by the angular momentum quantum number L, lowercase l, because that appears in the centrifugal potential. It's hiding inside this U of R, you see. So in effect, there's a different radial Schrodinger equation for each value L of the angular momentum quantum number. On the other hand, notice that the radial Schrodinger equation does not depend on the magnetic quantum number M. It's completely independent of that. So what this means is the energy levels that appear when you solve this, well, let's put it this way. There is in effect a different radial Schrodinger equation for each different value of L, because the effective potential changes. So we can think of solving not one radial Schrodinger equation, but a whole family of them indexed by L equals 0, 1, 2, 3, and so on. So it's convenient to if you want to plot energy levels, it's convenient to make a two-dimensional diagram that looks like this. We're going to have energy running in one direction and angular momentum running in the other direction. So let's just set up columns here. L equals 0, L equals 1, L equals 2, and so on, L equals 3. We'll set up columns. And when we solve the L equals 0 equation, we get some energy levels. Who knows what they look like? It depends on the potential. L equals 1, you get energy levels. L equals 2, you get energy levels, and so on. It could look something like this. This is the idea. As far as the energy levels themselves are concerned, they need to be indexed by L because the radial Schrodinger equation depends on L. But there's also a sequencing number here. You may number them n equals 1, 2, 3, or 0, 1, 2, 3. I don't care where you start the n value, but there's an n quantum number, which is basically just a sequencing number in this list. Now, there's a question about whether these energy levels are bound or whether they're in the continuous spectrum. Which one is it? It depends on the problem, actually. A common type of problems that occur in 3 dimensions is one in which V of R goes to 0 as R goes to infinity. And if that's so, it means that above the energy E equals 0, we have a continuous spectrum. So if this is very common, by the way, in atomic problems. So if that were the case, and this line here were E equals 0, then we'd have a continuous spectrum. I'll just indicate it here by, arrows going up like this for all the different L values. The L value, the different L values doesn't affect this fact that the continuum starts at E equals 0. The reason it doesn't is because the centrifugal potential, way back up here, wherever it is, right here, is a constant over r squared. So it goes to 0 as r goes to infinity. And if the true potential also does the same, then the total potential goes to 0 as r goes to infinity. And then E equals 0 then becomes the continuum threshold, and you get a picture that looks like this. So you may have some discrete bound states you see with negative energy, if this is what your potential looks like, and then a continuum above E equals 0. Now, the bound states have to vanish at r goes to infinity because they decay exponentially out in that region. And so by the theorem that I was just mentioning, it means that they're automatically are non-degenerate. The continuum states don't vanish at r goes to infinity. They go all the way out, and they tend to oscillate as you go out to infinity. But as I'll explain in a minute, due to boundary conditions at r equals 0, they're forced to vanish there. And so again, by that theorem, it means that they're non-degenerate. I'll explain that in just a minute, but the conclusion is that for both the bound states and the continuum states, the solutions of the radial Schrodinger equation are non-degenerate for a given value of energy E, and thereby proving that HL squared and LZ form a complete set of commuting observables. I'll come back to the bound states, why they're non-degenerate in just a minute. All right. So if the potential looks like this, then for a given value of L, in general, you've got some bound states and then a continuum. There's nothing that says that you have to have bound states. It depends on the potential. In some cases, you have bound states for some values of L and not for others. The nice example is actually the deuterium nucleus. Deuterium nucleus as a two-body nuclear problem. One of the particles is a neutron and the other is a proton. If I write it like that, so it's a two-body problem, and it's approximately a central force problem. It turns out that the deuterium has exactly one bound state in the L equals 0 class, and it doesn't have any bound states at all in any of the higher L's. So it has just one bound state altogether. That's kind of an extreme example of having, well, an extreme example would be to have no bound states, and there's some potentials for which that's true. So anyway, there's all kinds of possibilities of how this splits up. All right. Now, why are the unbound states non-degenerate? The reason has to do with the behavior of the, and by the way, when I'm speaking of the degeneracy here, to be clear, the degeneracy that I'm talking about is the degeneracy of the radial Schrodinger equation. So in whichever version of the two that I choose, I want to solve this to the given value of L, and I solve this and I find the energy levels. So these energy levels, let's look at their quantum numbers. Well, I said they should be labeled as N and L, where L gives you the class, angular momentum class that you're in, and N is a sequencing number. That's appropriate for bound states. For the unbound states, they're not quantized in N, but rather there's a continuum, and you want to probably use a continuous index here instead of N for those, but they're still characterized by L. All right, in any case, this is the degeneracies I'm talking about in terms of the radial wave equation. Allow me next to it, this is a bit of a digression, but I'm going to come back to where we are in a minute. Let's consider the behavior of the radial wave function when the radius is small. Let's look at Rn L of R as R goes to 0. Let's assume that I'll just write R of R, but it really means RNL, one of the eigenfunctions. Let's assume that this behaves as a power law. In fact, let's write it as a constant times R to the P power. Let's assume it behaves as a power law as R goes to 0 for small r. The dominant term looks like that. If we plug this into the Schrodinger equation, let's work out first of all the radial component of the kinetic energy. So we first of all have to compute R prime, and that goes as you see, A times P times R to the P minus 1. If I multiply by R, what I'm really doing is I'm marching myself through this operator, which appears here, right here in the radial Schrodinger equation, 1 over R squared DDR, R squared DDR. That's what I'm working through here. So r squared times r prime then goes as r prime one is leaving off the r squared. This one is ap times r to the p minus 1. If I multiply it by r squared, this raises the p plus 1. If I take r squared r prime and differentiate that again, that goes as a times p plus 1 times r to the p. If I then multiply by 1 over r squared, then this r to the p becomes r to the p minus 2. And then eventually I'll multiply by minus h bar squared over 2m in order to get the radial part of the kinetic energy. In fact, let me write this out. It becomes minus h bar squared over 2m times a times p plus 1 times r to the p minus 2. This is the radial part of the kinetic energy. Now then there's the centrifugal potential, which as I explained is also the angular part of the kinetic energy, and that's plus h bar squared times L plus 1 divided by 2m r squared times the radial wave function, which is a times r to the p. And then there's the potential energy V of r multiplied times a times r to the p, and that's equal to the total energy E times a times r to the p, where I'm just plugging in the leading form for the radial wave function. So this is what we get by analyzing the wave function when the version 1 of the radial Schrodinger equation when the radius r is small. Now the powers of r, which are smallest, are the ones that are dominate. Here's an r to the p minus 2. You can see the next term coming from the centrifugal potential also goes as r to the p minus 2 because it's r to the p divided by r squared. This term involving the true potential depends on the behavior of V. Usually the worst behaved potentials that we get are Coulomb potentials that go as 1 over r at the origin. It doesn't have to do that, but it's usually either as bad as 1 over r or else not as bad as that. It tends not to go faster than that. And so if that's the case, if we assume that, that covers the important case of the Coulomb potential, then the potential energy term diverges as 1 over r to the p minus 1, as you can see, or it behaves like 1 over r to the p minus 1. And that goes to 0, that is smaller than 1 over r to the p minus 2 as r gets small. As far as the total energy term, it only goes as r to the p, and that's even smaller still. So the conclusion is that when r is small, the true potential and the total energy term don't contribute. They're insignificant compared to the other two terms, which then have to balance each other out. So let's do that. Let's set what's left over equal to 0 here. And if you do, you see you can cancel the minus h bar. You can cancel the h bar squareds over 2m, which are common factors. You can cancel the r to the p minus 2, which is there and there. And you can cancel the a, which is there and there. And the result is you get an equation that says that p times p plus 1 is equal to L times L plus 1, which gives us an equation to solve for the power, which is the behavior of the wave function at small r. All right, so let's analyze that. Well, p times p plus 1 equals L times L plus 1 has two solutions. One is p is equal to L, and the other one is that p is equal to minus L minus 1, as you can check. And so what that means is that the radial wave function R of r for small r as r goes to 0 behaves like either r to the L or else r to the 1 over r to the L plus 1. Those are the two choices. Now L, of course, ranges from 0, 1, 2, 3 out to infinity. That's the quantum number of L. And so 1 over r to the L plus 1 diverges at the origin. If you take the case L is greater than or equal to 1, this goes at least as 1 over r squared, which means when you square it to get the probability, you get 1 over r to the 4th. And that gives you a non-integrable singularity at the origin, which means that the scalar product of the wave function with itself is going to be equal to infinity because of the divergence at the origin. And so this has to be rejected because you can't normalize the wave function. You have an infinite amount of probability at the origin. On the other hand, if L is equal to 0, then this goes as 1 over r, and in that case, the Laplacian del squared of 1 over r needs to be interpreted as something times a Dirac delta function of r vector, like that 3D delta function. And so this then appears in the kinetic energy, and you can't solve the Schrodinger equation unless that delta function is balanced out by, it has to come from the potential energy. So if your potential does not contain delta functions, and let's assume it doesn't, then this is not allowed either. In any case, the net conclusion is that this 1 over r to the L plus 1, under the circumstances I've just described, have to be rejected on physical grounds. And so we conclude that the r to the L, and this is an important rule, is that the radial wave function, which is parameterized by the quantum number L, behaves as r to the L power when r goes to 0, when r is small. That means that the function f of r has to go as r to the L plus 1. And therefore, this goes to 0 as r goes to 0 for all values of L. And so if I go back to the version 2 of the radial Schrodinger equation, and that's the version I want to use because I want to invoke these theorems that we had earlier for 1D quantum mechanics. The wave function f of r version 2 must go to 0 at the origin for both bound states and unbound states. For bound states, it goes to 0 as r goes to infinity as well. But in any case, because it goes to 0 somewhere on the r axis, it means that the wave functions are non-degenerate. And that's the proof of the non-degeneracy of these. They're non-degenerate regarded as a solution of the 1D radial wave equation. All right. Now, that doesn't mean that the wave functions in 3 dimensions are non-degenerate. Before I draw the energy diagram, let me clear a space here on the paper. The reason is that the total wave function psi is equal to, let's leave some room for quantum numbers, it depends on r, theta, and phi. It's the radial part, and the radial part depends on n and L of r. Depends on L because that's the radial wave function is parameterized by that, and it depends on n because that's the sequencing numbers of the states, times the YLM of theta and phi. But the energy levels only depend on n and L because the radial wave function was independent of the magnetic quantum number. So psi depends on 3 quantum numbers, n, L, and m, like so. This is how it works for bound states. If it were unbound states, the discrete quantum number n would be replaced by a continuous index, but the L and the m would still be there. And you'd have the same conclusion that it looks like a radial wave function times the YLM. All right. Now then, what we see then is if you look at the 3-dimensional wave functions, there is a degeneracy because of the magnetic quantum number. The m runs from minus L up to plus L. So in other words, by including the YLM factors, for example, if I took L equals 1 here and I have one of these energy levels in this column, this is actually 3-fold degenerate when you multiply by the YLMs because of the magnetic quantum numbers, the m values. The L equals 2 column would give you 5-fold degeneracy and so on. So all central force problems have a degeneracy of 2L plus 1 because of the magnetic quantum number m running from minus L up to plus L. And so that's the enumeration of degeneracies of all central force problems. There's a physical reason for that degeneracy, and it is simply the rotational invariance of the problem. That's what does it. The magnetic quantum number, of course, is the quantum number of the operator LZ. This is the same thing as z hat dotted into the position, the angular momentum vector L. Of course, that's what it is. This is the projection, LZ is the projection of the angular momentum onto the z-axis. If you took your system and you rotated it, you can think of this classically, if you will, it gives the right idea. You would rotate the L vector, the angular momentum would rotate along with the system. And therefore, it would change the projection of the angular momentum onto the z-axis. On the other hand, if you have an isolated system, which is therefore invariant under rotations, the energy cannot depend on the orientation. And therefore, the energy cannot depend on this projection of the angular momentum. And that's the physical reason why these energy levels are turning out to be independent of the magnetic quantum number. All right, so its rotational invariance explains why we have this 2L plus 1 fold degeneracy in the magnetic quantum number m. Is it possible that there are further degeneracies? If we go back to my diagram here, the answer is yes, it is possible because you could have degeneracies between different L values. One of these levels over here might coincide with one of those levels over there. However, for a randomly chosen radial potential, this is not very likely And the reason is that when you change the potential because of the centrifugal potential and going from one of these columns to the next, in effect, what you're doing is creating a new one-dimensional Hamiltonian, which is independent of the old one. And so you in effect, you kind of have random levels on one column, another random set in another. And the probability that the two of them are going to coincide exactly is very small. In fact, it's really zero. Of course, they could come very close together. And in fact, they do in practice, but for randomly chosen potentials, they don't coincide exactly. So for what you might call randomly chosen centrifugal potential, the only degeneracy you have is from the magnetic quantum number due to rotational invariance, and that's all there is. However, as we will see, there are special problems, special central force potentials, for which there are systematic degeneracies amongst the different values of L. And this happens notably for the hydrogen atom, but it also happens for the 3D harmonic oscillator. The 3D harmonic oscillator is a potential where V of R is equal to m/2 times omega squared times r squared, where r squared is the three-dimensional radius squared. In other words, it's x squared plus y squared plus z squared. This is a central force problem. It's also a three-dimensional oscillator in which the frequencies in the three directions are all equal to one another. Such oscillators actually occur in real physical problems. For example, the vibrational modes of the methane molecule involve such a three-dimensional isotropic harmonic oscillator. Other places too. So there are examples, including both this 3D harmonic oscillator and the hydrogen atom, in which there are systematic degeneracies amongst different L values. The reason why that happens is because those problems have extra symmetry that goes beyond rotational invariance. If I make a little table here, is it for a random potential, by that I mean central force potential V of R, versus the Coulomb potential versus the 3D isotropic harmonic oscillator. The Coulomb potential goes like 1/r, and 3D oscillator goes like r squared, and the V of R here is just a random V of R. The symmetry group is just simply SO3 for a random potential. It's just ordinary rotations. That's what we've been talking about. Turns out for the Coulomb potential, it's SO4. There's a larger symmetry group. And for the 3D oscillator, it's SU3. It's a larger symmetry group. And so in those two special cases, the systematic degeneracies amongst the different L values is due to the fact that the problem has extra symmetry that goes beyond rotational invariance. I'm not going to belabor this very much in this course, but I'm pointing it out because it is an important fact for this course that systematic degeneracies are caused by symmetries, and vice versa. Symmetries cause systematic degeneracies. And so symmetries is an important theme of the course, and degeneracies are a clue to the existence of symmetries. This, by the way, has played a role in the history of physics. I mean, physicists have on occasions observed degeneracies or near degeneracies and deduced, therefore, that there's a symmetry or perhaps a broken symmetry lying behind the physics. This notably happened in the case of isospin, ultimately explaining why the neutron and the proton have almost equal masses, which was later generalized into the SU3 or quark model of nucleons, which is a basis now of QCD, the strong interactions. Okay, anyway, this is how it works out for central force problems. All right. I think unless I'm forgetting something, that's the main stuff that I want to say about some of the basics and some of the setup of central force problems, the degeneracies, the assignment of quantum numbers, radial wave equations, behavior at the origin. Are there any questions about this before I go on to the next topic? If not, then the next topic is to look at an example, central force motion, logical to do at this point. The simplest example is a free particle. So for a free particle, the potential V of R is equal to 0. In that case, we don't have to worry about the mass of the object producing the force field because there is no force field. And so the one body problem is accurate and exact. So we have a one body problem for the central force for the free particle. In this case, the version 1 of the radial Schrodinger equation is easiest to work with. It's h bar squared over 2m, 1 over r squared ddr times r squared d of capital R with respect to lowercase r, plus L times L plus 1 over h bar squared over 2m r squared times capital R of R is equal to the energy times capital R of R. And for a free particle, there'll be no surprise that the energy is greater than or equal to 0. By the way, if the true potential is 0, the effective potential, let's start plotting effective potentials, U of R. The effective potential consists of only the centrifugal potential. And the centrifugal potential looks like this for different values of L, L1, L2, and L3. If these are L1, L2, and L3, and increasing, as L increases, the centrifugal potential moves out. Like as it dies off as 1 over r squared, you see as r goes to infinity. In fact, it's proportional to 1 over r squared. It diverges as 1 over r squared. Positive in divergence as r goes to as r goes to 0 along the x-axis. In any case, you have the effective potential looks like this. Now, this differential equation we usually express. Oh, and by the way, what these potentials show you is that there's no bound states. There's no well for the wave function to sit in. This is all strictly repulsive potential going out to infinity. Particle can come in from infinity, climb up this potential well, reach a turning point, reflect, and go back out. That's a WKB picture, but it conveys the right ideas that all the solutions are unbound. In some sense, they're scattering. So all of them are scattering solutions. So therefore, it's no surprise the spectrum consists of just positive energies. Now, if we take the energy E, it's convenient to express it in terms of an equivalent wave number I'll call K by writing E is equal to h bar squared K squared over 2m like this, or equivalently K is equal to the square root of 2me over h bar. And we'll introduce a dimensionless radial variable I'll call rho, which is equal to K times R, like so. And making these substitutions into this Schrodinger equation, it turns into kind of a standard form, which is 1 over rho squared dd rho of rho squared times the dr d rho plus the quantity 1 minus L times L plus 1 over rho squared. You can see that's the centrifugal potential there, times R equals 0. And this is a standard equation, or this is the equation for standard functions in mathematical physics, the so-called spherical Bessel functions. So the solutions are that R of R is equal to either, they come in two forms if you look them up in the references. One is called a JL form, JL of rho, and the other is called a YL of rho, like so. Two types of spherical Bessel functions. You can read about these in Abramowitz and Stegun, for example. If you look at the properties of these Bessel functions, you find that for small rho, JL of rho goes like rho to the L, whereas YL of rho goes like 1 over rho to the L plus 1. This is when rho is small. Rho is dimensionless numbers, so let's say rho is much less than 1. These conditions hold. So what you can see is the JL of rho are the solutions which we decided were physically allowed. That's where the radial wave function goes like R to the L at the origin, whereas these are the ones that have to be rejected on physical grounds. Actually, we'll see later when we do scattering theory that the Y's are not always rejected, but let's just say for now that if you're really talking about a particle that's free everywhere, all the way down to the origin at R equals 0, then the Y solutions have to be rejected because they diverge there. They diverge there badly enough to be rejected. Okay, so the radial equations consist of just the JL types, and therefore they're non-degenerate as we expected on general grounds mentioned earlier. This means that the wave functions for a free particle can be written like this: is psi of K, L, and M of R, theta, and phi. I'm writing an effective wave number K here is equal to J sub L of KR for the radial part times the YLM of theta and phi. And we'll deal with these wave functions at greater length when we come to scattering theory. It's interesting to plot the radial wave, the spherical Bessel functions, the J-type spherical Bessel functions. Those are the ones that matter. Here, let's plot them here. Let's plot JL of rho. give you some feeling of what they look like. For L equals 0, you get a function that starts at a constant up here. And I'll try to sketch it as best I can. It comes down and then it oscillates like this. And the amplitude of the oscillations gradually decreases as it moves further out the rho axis. So you get something like this moving out rho, like so. If you take J1, this is for L equals 0. If you take L equals 1, it starts off as a straight line. As I indicated, it has to be proportional to rho. It rises up like this, reaches a maximum, comes down like this, and then oscillates like this, kind of out of phase with the previous function doing this kind of a thing, like so. This is L equals 1. If I take L equals 2, it's a quadratic function here, rises up like this, and starts to do this. L equals 2 starts off as a cubic function near the origin, and then does this kind of a thing, and so on. So you get this kind of pattern here. These are pi/2 phase shifts amongst these different JLs. So this is a plot then of a bunch of JL type wave functions. I didn't mention this. I meant to mention this back when we derived the general behavior that Rn(L) of R, or whatever quantum number you want to use for the energy, doesn't matter. It's the L dependence here that counts. But this goes as R to the L. What this means is that if I plot R sub L of R, like this, as a function of R, for L equals 0, it's constant near the origin because it goes like R to the 0 power. For L equals 1, it's a straight line because it's proportional to R. For L equals 2, it's a parabola because it goes like R squared. For L equals 3, it's a cubic function that lies down like this, L equals 3. And what you can see is that from this behavior near the origin, you can see that as L increases, the function lies down more and more flatly near the origin. What that means is if you pick some small region around the origin like this, the probability of finding the particle in this small region decreases with L. As L goes up, the probability goes down. In fact, since it goes like R to the L, if the size of the region is A, the value of the wave function in that region is bounded by A to the L power, where A is a small number. What this means is the wave function itself decreases exponentially with L. So does the size squared does too. It goes like R to the 2L or A to the 2L, even faster. And so this is an important qualitative phenomenon of radial wave functions. For example, it means that the probability of finding an atomic electron inside the nucleus of an atom decreases rapidly with the L quantum numbers. And in fact, it's practically 0 unless L is equal to 0. We'll say more about that later on in some applications. All right, but in any case, in the case of the free particles, you can clearly see the behavior here near the origin where it's constant for L equals 0, linear here, quadratic, cubic, and so on. All right. If I took the J sub L and I plotted it for just one value of L, which was not too small, it would look like this. Here's rho, and here's JL of rho. Radial wave function for a free particle. It kind of goes out like this. It's very small near the origin, and then goes out some distance, and then it rises up like this, and it has a maximum, and then beyond that, it oscillates like this with amplitude that decreases as you move on outwards. And if you look at that, you can recognize that this looks like WKB theory. Looks like here's a turning point somewhere around this maximum here. There's exponential decay as you move inside. This should be some kind of classically forbidden region. Whereas out here, you've got a classically allowed region where the wave is traveling. Well, there's a good question which arises is how can you have a turning point for the case of a free particle? And I want to give you a simple argument for how you can understand that. First of all, based on classical mechanics. Let me draw the XY plane here, and let's draw a typical orbit of a free particle. That's, of course, just a straight line. That's all it is, just goes like this. But let's say this particle has some momentum p. It's a free particle, so it's got a fixed momentum p vector in the same direction and everything. It's also got an angular momentum L. The angular momentum can be determined by looking at the minimum distance of approach. Let's call that R0. The angular momentum L then is equal to the p, which is the momentum of the particle times R0. All right. Now then, if we then take these classical relations and convert them into quantum mechanics, capital L can be identified with the L quantum number times h bar. The momentum P can be represented as h bar times k, and R0 I'll just leave as R0 like that. So what this implies then is that KR0, which is what we're calling rho zero, because remember rho is equal to K times R, is equal to L. You see this particle here, the classical particle does not come closer to the origin than R0. So there's a rho zero here, out here, some rho zero, and this is approximately equal to L for rho sub L. That's what it is. It's really representing the fact that the classical particle can't come any closer than that. If I draw a circle in my classical diagram here of radius R0, and then draw other orbits, other classical orbits that have the same value of L, but different momentum, which of course are vectors like this, what you get is a family of classical orbits that are all tangent to this circle like this. There's a family of them. And the circle itself is the envelope of that family. If we take if we move along a radial line outwards from here, like this in this classical picture, and then we plot along the radial line the spherical Bessel function of the quantum problem that corresponds to it, what you get is 0 inside here, then rising up to a turning point at this R0 radius, and then oscillations out beyond that. That's kind of the idea. So I'm giving you this because this WKB theory, as you see, without doing much work, gives you a qualitative understanding of why the spherical Bessel functions do what they do and why they look like the way they look. All right. Okay, so that's enough for the free particle. Now then, for other kinds of central force potentials, unless the mass of the force object itself is extremely large, we really ought to worry about what happens when its mass is not infinity. And if that's the case, then we really have to deal with a two-body problem and not a one-body problem. So let's address that issue now. Let's take our coordinates x, y, and z, which we can now think of as lab coordinates. And let's put two particles in here. Let's put one at position, let's call it x1, and another particle out here and put it at position x2. Like so, we have two particles. So draw the line between them like that. And they've got masses m1 and m2, which will allow to be different. Then the Hamiltonian for the system is the total energy of the system, which is the kinetic energy of particle 1. It's p1 squared over 2m1 plus p2 squared over 2m2 for the kinetic energy of particle 2, plus the potential. And in order to make a central force problem, we will assume the potential is a function only of the distance between the particles. So it's a function of the absolute value of x2 minus x1, like so. So this is now a two-body Hamiltonian. Central force problem now still, but it's two-body Hamiltonian. This should be m1 here. How do we solve this? Well, we solve it by doing a change of coordinates. We go to center of mass and relative coordinates. The relative coordinate we'll define as r is equal to x2 minus x1. It's obvious on the diagram here what that is. It's this direction arrow like that. This is the vector r, like so. And then we introduce the center of mass coordinate, capital R, which is equal to m1 times x1 plus m2 times x2 divided by the total mass m. Capital M here will be understood to stand for the total mass m1 plus m2, like so. All right. So let's carry out this coordinate transformation on the Schrodinger equation or on the Hamiltonian. Now, in order to transform the Hamiltonian, it's obvious that we need to transform not only the coordinates which appear in the potential energy, but also the momenta. How do we do that? Well, let's take, for example, momentum P1, which is a momentum of particle 1. That's the operator minus I h bar partial with respect to x1, because that's how it is for spatial degrees of freedom. Now, on the other hand, x1 is a function of big R and small r. We can get that by inverting these equations and solving for x1 and x2 as a function of big R and small r. So by the chain rule, I can write this way as minus I h bar, which I'll factor out. And this derivative ddx1, that's the same thing as partial of let's do it, big R with respect to x1 times partial with respect to big R plus partial of small r with respect to x1 times partial with respect to small r, like so. And if we write this out, it becomes minus IH bar. Now partial of big R with respect to x1, you can see is m1 over m, over capital M. Partial with respect to big R. And for the second term, small d of small r with respect to x1 is equal to -1. So we get minus partial with respect to small r. Now let's define operators I'll call capital P, which is minus IH bar dd big R, and lowercase p, which is equal to minus IH bar partial with respect to lowercase r. If we do this, then these terms here can be written as m1 over capital M times capital P minus lowercase p. And so we get the equation then, to summarize, small p1 is m1 over capital M times capital P minus lowercase p. And we can do this similarly for the second m2, p2, and we find this is m2 over capital M times lowercase p plus capital P. I think it's a plus sign in here if I'm not mistaken. Yes, it is. All right, and so we now have transformations of the position coordinates here and the momentum coordinates like that. And we can invert both of these to solve for the new coordinates as functions of the old and vice versa. And to save you the algebra of doing that, I have done it for you. If I can find my magical page, which has it. Don't tell me I've lost it. I did it for you. What did I do with it? Just a minute here. Let me find it. Summarize all this. I did do it. It's not there. It's not there. Where is it? Did I throw it away? Good grief. Excuse me a second. Let me see if I can find this missing page. I can put it over there either. What did I do with it? Oh, I'm sorry. I don't know what happened to it. I'll check again here. Oh yeah, here it is. It's right here. It was right before me. I just wasn't looking. All right, here we go. So what I've summarized here in these four boxes are these transformation formulas, both the forward formulas and the inverse ones. This is the original definition of the center of mass and the relative coordinate. These are the transformations of the old momenta as functions of the new. And by inverting them, I get these two equations across like this. We know what the x1, x2, and p1 and p2 are. Those are the positions and momenta of the particles in the lab frame. What about the new ones, the capital P and the capitalized, well, excuse me, the small r, big R, and the small p and big P, what are those? Well, the small r and big R are clear. I just explained what those are. It's relative and center of mass coordinates. What about the corresponding momenta? You can see that the momentum big P, which is conjugate to the center of mass position, is the total momentum of the two particles. It's P1 plus P2. The momentum lowercase p, which is conjugate to lowercase r, because it's minus IH bar d of lowercase r, is more difficult to interpret. It's, as you see, it's m1 p2 minus m2 p1 over the total mass. And what does that mean? There's various interpretations of this p, and I'll just give you one of them. It is that if you go into the center of mass frame, then this momentum p is to within a sign anyway, is the momentum of one or the other of the two particles. I mean, in the center of mass frame, by definition, the total momentum is zero. So the momenta of the two particles have to be equal and opposite each other. And this p is the momentum, or minus it is the p of the is the momentum of those two particles in that frame. Now it's fairly easy to see this, because if I set capital P equals to 0, then P1 and P2 are equal and opposite. So for example, if I make P1 equal to minus P2, then you see I get an M1 plus M2 times P2 over total M. That just turns into P2. So in that case, this P is the same as P2. That's what I'm saying. In the center of mass frame, that's what it is. Well, in any case, this gives us physical interpretations of these variables. Now, having done that, having made that interpretation, we can now do the algebra of transforming the Hamiltonian. Here's the Hamiltonian where we started with up above, right here, like so. We have explicit formulas for the P1 and P2 as a function of the new P's right here. And if you plug them in and do the algebra, here's what you get. You find the Hamiltonian is big P squared over twice big M plus lowercase p squared over twice 2 mu, which I'll define in a minute, plus the potential energy V. Potential energy V is easy because it's just the distance between x2 and x1. That's just the magnitude of the relative position vector, lowercase r, as you see in your diagram here. So this just becomes V of r, like so, okay? So in making this transformation, the total Hamiltonian breaks up into two terms, one of which I'll call HCM for the center of mass, and one which I'll call HREL for the relative motion. By the way, the mu I haven't defined yet, but the mu is the reduced mass, which is defined as the harmonic mean of the two masses of the two particles. As to say, 1 over mu is equal to 1 over m1 plus 1 over m2. It's called a harmonic mean. And that's what appears here as an effective mass in the relative Hamiltonian. I'll say more about that in a minute. As far as the center of mass Hamiltonian is concerned, you can see it's nothing but that of a free particle. This corresponds to the classical fact that a system of the type I just described, central force problem involving two bodies, the center of mass moves on a straight line with constant velocity. It's basically, it's a free particle in those degrees of freedom. The H relative gives us the dynamics of the system relative to the center of mass, which is why it's called HREL here. This Hamiltonian is, as you can see, is an effective one-body central force problem of the type that we had earlier when we took the central mass to be infinite. Except now we haven't done that. We've allowed for finite central mass. There's a couple of changes, however. One is a reinterpretation of the variables. R is not the distance from the origin; it's rather the distance between the two particles. And P here is not the momentum of the orbiting particle, but it's rather, as I explained earlier, it's the momentum in the center of mass frame. Also, the true mass of the orbiting particle has been replaced by mu, which is the reduced mass. It's worthwhile mentioning that if the two masses M1 and M2 here are very different from one another, then the reduced mass is approximately equal to the smaller of the two of M1 and M2. For example, in hydrogen, in which the proton mass is much bigger than the electron mass, let's say M2 is the electron, if that's the case, then mu is approximately equal to the electron mass. On the other hand, if you have like a diatomic molecule, like O2, where the two atoms have equal masses, M1 and M2 are equal to one another, then mu is equal to M over 2, and they're all comparable to one another. All right, in any case, this is what we get. Now then, this is a great progress because the new Hamiltonian is separable is separable because of the separation of the first term, which depends only on the relative, on the center of mass coordinates, and the second one, which depends only on the relative coordinates. These two Hamiltonians, HREL and HCM, commute with one another because they depend on different sets of degrees of freedom. I didn't talk about the commutation relations, by the way, but under these coordinate transformations or operator transformations that I gave you up above here, this in fact is a canonical transformation, which means that the Heisenberg-Born commutation relations, which apply between x1, x2, and p1 and p2, are reproduced by the new variables. So that small r with small p has got a IH bar Kronecker delta ij commutator, and likewise for large R and large P, but crossing over between these two or among these two, the commutators are all 0. This just follows from the fact that these P operators are defined as minus IH bar times the corresponding derivative with respect to the corresponding position operator, and that just leads to the usual IH bar delta ij commutators when you let them act on wave functions. But in any case, the canonical commutation relations still apply for the new variables. So in classical mechanics, that's called a canonical transformation that does that. And that in turn means that HCM commutes with HREL. So if we separate the Schrodinger equation, we get two separate Schrodinger equations. We get HCM. So here's the idea, is we let the wave function for the whole system, let's call it capital psi. This depends originally on the two coordinates of the two particles, x1 and x2. Let's re-express this in terms of center of mass and relative coordinates and write it as just capital psi of big R and small r. And then let's assume that this can be factored into a wave function of big R times another way, which I'll call capital phi, times another wave function of small r that I'll call lowercase psi. We assume this for the sake of separation of variables. I haven't talked much about separation of variables in this course because you've seen it before in your other courses, but one always makes an ansatz or a guess that the wave function can be represented in this form, like this, when you do separation of variables. One of the main things that I want to point out here is that we are not assuming that the general wave function, two-particle wave function, has this product form. Far from it. All we're doing is we're seeking solutions that have this product form. And it turns out that if we can find enough of them, then we can construct arbitrary solutions which are not of such a product form. That's the logic in separation of variables. In any case, making this assumption and plugging in the Schrodinger equation, we get separate Schrodinger equations for the two parts, the two factors. There's a center of mass form. Well, let me write it this way. It's p squared over 2m acting on phi of r is equal to a center of mass energy, ECM times phi of r. And then there's a relative Hamiltonian, which I won't bother to copy out, acting on psi of r is equal to a relative energy multiplying psi of r, like this, psi of r, our vector. And the total energy that appears in the total Schrodinger equation is the sum of these two energies, E center of mass plus E relative. The center of mass Schrodinger equation is trivial because it's just a free particle. Again, this corresponds to what happens in classical mechanics for the time evolution of the center of mass. And so solutions are easy to write down as capital phi of the center of mass coordinate is just given by a plane wave, e to the I capital P dot capital R divided by H bar, like this. This is an eigenstate of the total momentum of the system, like this, and it's also a free particle solution. We don't have to use these free particle solutions. We could separate this center of mass wave function in spherical coordinates, and then we'd have spherical Bessel functions for the capital phi. You can do that if you want to. But in any case, the free particle solutions, so they're kind of trivial for what we wanted, for the main points we want to make here. As far as the relative motion is concerned, let's look at that. That is, as I mentioned earlier, now becomes a pseudo or effective one body problem, which we talked about at some length earlier in this lecture. And so we can use all the techniques, the behavior of the wave function at zero and so on, in order to understand this wave equation. As long as you're thinking physically, however, it's worthwhile remembering that in this relative wave equation, that variables like r here, lowercase r here, I mean, for example, in hydrogen atom, you'd look at this equation and you'd say, oh, r is the position of the electron. Well, actually, it's not. It's the position of the electron relative to the position of the proton. In other words, dynamically speaking, really, it's a function of the positions of both particles. And the same thing applies for the momenta too. That depends on the momenta of both particles. It just looks like a one body problem. All right. Anyway, so we've reduced this now to one body problems, and we can now talk about solving them, doing some examples of solving them. All right. So that's kind of the second phase of lectures, the lecture tonight. Let me pause here and ask if there's any questions about this part of it. All right. If not, I want to move on to the next phase, which is to look at some more examples. The first example that I'd like to deal with is the case of a rigid rotor. Let me make sure I'm not losing my summary sheets anymore. Let's talk about the case of a rigid rotor. A rigid rotor may not look like a central force problem, but there's an interpretation in which it is. It consists of two masses, M1 and M2. They don't have to be equal. One can be bigger than the other one. Connected by a massless rigid rod whose length, let's call it R0, is fixed. This is obviously an idealization of what happens in the real world, and I'll say something about that. But we can think of this as being an example of a central force problem, because if you imagine there's a potential V of R which is sharply localized around some radius r0, like this rises rapidly away from r0, then that confines the masses m1 and m2 to be, to an approximation anyway, to be at a fixed distance r0 from one another. And it gives rise to a what is in effect a central force problem. Before we do the quantum mechanics of the rigid rotor, let's look at the classical mechanics. One of the things you learn in high school physics is that the energy of a rigid rotor is equal to 1/2 the moment of inertia times the square of the angular velocity. On the other hand, the angular momentum is equal to I times omega. So you can write this in terms of the angular momentum as L squared divided by 2I, where I is the moment of inertia. Now, the moment of inertia, in fact, is equal to the reduced mass of these two masses, m1 and m2, multiplied times r0 squared, where 1/mu is equal to 1/m1 plus 1/m2. And I won't derive that because that's all classical mechanics and you can check it for yourselves. But in any case, what this classical mechanics suggests is that, well, what the picture suggests, first of all, is that if we wanted to know quantum mechanics of the rigid rotor, we ought to have a wave function that depends on the angles theta and phi, but is independent of the radius r because that's been fixed. So we can think of the wave function now as being a wave function on the sphere, unit sphere or something. It basically gives us the wave function or probability amplitude for the direction of the rigid rotor. Maybe we can draw an arrow in here connecting m1 and m2. It's the direction of this radius vector r, whose magnitude is fixed, okay? As far as the Hamiltonian is concerned, it would be a good guess to borrow the energy from the classical system, which is L squared over 2I, without changing what we write down the formula, but reinterpreting L squared now as the usual angular momentum operator. And if we do this and we want to solve the Schrodinger equation H psi equals E psi, the solution is immediate, is that the psi wave function, psi of theta and phi, is nothing but a YLM of theta and phi, because that's an eigenfunction of L squared. And so then the energy then is equal to the L squared acts on the YLM, brings out the eigenvalue, which is L times L plus 1 H bar squared over 2mr squared. Excuse me, over twice the moment of inertia, 2I, that's what comes out. Except for the rigid rotor, the moment of inertia is I times mu naught squared. So this is L times L plus 1 H bar squared divided by 2 mu naught R squared. Like so, excuse me, let's do it right. Let me do it right. It's equal to L times L plus 1 H bar squared times mu times R naught squared. There's no naught on the mu. I'm thinking E and M SI units for some weird reason. Anyway, mu times R naught squared. It should be times 2. That's the moment of inertia times 2 in the denominator there. Now look at this energy that comes out. This is an energy eigenvalue. We could also look at the operator. This energy is in the interpretation I've explained already. This is nothing but the rotational part of the kinetic energy of the rigid rotor. And that makes sense because the rigid rotor doesn't have any doesn't have any radial part of the kinetic energy because the radius is fixed. The angular part is all there is. And so this energy that I've just derived in this way, it's kind of a hand wavy procedure I've been through, but you can see that this energy is nothing but the centrifugal potential it's a special case of the centrifugal potential. We'll come back to that later. It's interesting how it works out. All right. So in any case, this is then are the wave functions and energy levels of a rigid rotor, in a three-dimensional rigid rotor in quantum mechanics. One more thing to mention is there's a 2L plus 1 fold degeneracy because M ranges from minus L to plus L, and the YLMs, the energy doesn't depend on the magnetic quantum number, again, because of rotational invariance. All right, now then. Rigid rotors are an idealization, obviously, that don't exist in the real world, doesn't exist in the real world. But diatomic molecules do exist, and they are to some approximation are rigid rotors. And I'd now like to explain the sense in which diatomic molecules are approximately rigid rotors, how it deviates from that, and how it connects with this simple theory of rigid rotors that of a rigid rotor that I just laid out. So let's change the problem now. And let's talk about diatomic molecules. So we can picture a diatomic molecule in a ball and stick kind of a picture as being two atoms connected by a rod. It's not a rigid rod now, but let's say connected by a rod. These atoms are distinct. Let's make them distinct. In fact, an example that I've worked through in the notes is that of carbon monoxide. I wanted to make the two atoms different from one another. That's why I chose CO. The mass of the carbon atom is pretty close to about 12 times the mass of hydrogen. The mass of the oxygen atom is about 16 times the mass of the hydrogen atom. Let's denote the reduced mass by capital M rather than mu as I've done before. So this is 1 over MC plus 1 over MO is equal to 1 over M. And if we do this, then we find that the capital M, which appears here, is about 7 times the mass of the hydrogen atom, something like that. M is, I'll write it again, is about equal to 7 times the mass of the hydrogen atom. The hydrogen mass is about 2,000 times the mass of the electron. So very roughly, this is about 10 to the 4th times the reduced mass of this molecule is about 10 to the 4th times the electron mass, which I'll denote by lowercase m. I switched to using capital M for the reduced mass rather than the symbol mu that I was using a moment ago, because I want to contrast the reduced mass of the molecule, which is of the order of a nuclear mass, with the small mass of the electron. It's a ratio of 10 to the 4th. Big and small masses, that's the idea. So M over capital M here is about 10 to the minus 4. And this is a small parameter which appears in the analysis of molecules. Other small parameters that appear is the square root of the mass ratio, M over M to the 1/2 power, which is about 10 to the minus 2, or about 1 in 100, or the mass ratio to the 1/4 power, which is about 1/10, 10 to the minus 1. And we'll see these various parameters appearing in the analysis of the molecule. Now, let me proceed. To analyze the diatomic molecule as a central force problem, then we obviously need a potential. So let me say something about the potential energy. Potential energy, I'll just begin by sketching it. Here's the axis here. Here's the potential. Here's a radius r. We have V of r as potential energy. It rises rapidly to large values at small r, then it goes down like this, goes negative, creates a well, and then the well rises up and has a long tail that goes off and asymptotes to 0. The potential energy for diatomic molecules, for essentially all diatomic molecules, looks like this. The shape of the curve is not exactly the same for the molecules, and the parameters of the curve are not exactly the same, but it basically looks like this. Qualitatively, this is correct. This curve has a couple of parameters I want to point out. One is the well depth, which I'll call minus V naught. Another one is the position of the minimum of the well, which I'll call that R naught. That's obviously the equilibrium radius in this potential. The physics of this potential, well, first of all, the mathematics of this potential is hard, and I can't go into it, so I won't go into it. There's no simple formula for this curve. But the physics of it is fairly simple, and it's easy to understand where the curve comes from, or how it comes about. In the first place, at small radii, where the potential goes large, the reason it does so is because as you bring the two atoms close together to one another, their electron clouds start to overlap. And in effect, what you're trying to do is to cram a bunch of electrons into a limited region of space. It's like a particle in a box, or a box potential, if you start adding electrons to a particle in a box, as they go in, because of the Pauli principle, subsequent electrons have to go into higher and higher energy levels. And so it takes more and more energy to add each electron as you go in. Furthermore, if you try to compress the box by squeezing the walls together, the energy levels move further apart. And so all the electrons move into higher energy states, and it takes work to compress the box. This means that the degenerate electron gas that you've got in the box has a pressure even at 0 temperature. I'm assuming you're familiar with all these facts from your Stat Mech course, and where you've worked all this stuff out in detail, but that's the basic idea. Now here we don't have walls confining the electrons, but there is the electrostatic force of the nucleus, which pulls the electrons in that play somewhat the same role. so that if we move these two atoms together in such a way the electron clouds overlap, the new electrons, which are being crammed into the same spatial region of space, have to move into higher and higher energy levels. And that's what creates this repulsive force here. It's in effect the pressure of a degenerate electron gas that's created by trying to force the atoms on top of one another. On the other hand, if the atoms are far apart so the electron clouds don't overlap very much, what they do is they create each atom creates an electric field which polarizes the other atom, creating a dipole moment. And so you've got a pair of dipole moments mutually induced into one another, pair of dipole moments, and then these interact by dipole-dipole electrostatic interaction. And that dies off with distance. So this tail out here is an electrostatic dipole-dipole interaction. That's mainly what it is. That dies off basically as a power law of R moving out that direction. So there's these two effects, attractive at large distances and repulsive at short distances, and they compete with one another at intermediate distances to give us the minimum of the potential well like this. All right. The specific numbers for carbon monoxide are worth looking at. The V0 is about 11 electron volts, and the R0 is about 1.1 angstroms. In case you don't know, an angstrom is 10 to the minus 8 centimeters, which is 10 to the minus 10 meters. Anyway, an angstrom is about the size of an atom. Anyway, these are the numbers you get here. Now then, since we don't have an analytic formula for the potential, I'm gonna make do with order of magnitude estimates, but using dimensional analysis. The dimensional analysis is based on the fact that this potential energy involves the dynamics of the two electron clouds as they're brought further apart or closer together in the dynamics of the diatomic molecule. There are only three fundamental constants that go into the dynamics of the electron cloud. They're the charge of the electron, the mass of the electron, and Planck's constant. The speed of light does not enter into the list because the electron motion is non-relativistic, and we'll show in a minute in a minute, nope, not in a minute, it'll be next lecture, next Tuesday, we will show that that is the case, that the electrons are non-relativistic. So there's no speed of light in this. Now it turns out that out of these three constants, E, M, and H bar, it's possible to construct a unique distance, a unique time, a unique energy, momentum, angular momentum, et cetera, that are constructed strictly out of these constants in a unique manner. This all comes from dimensional analysis. And I summarize that here. Here's what it is. Dimensional analysis with these three constants, E, M, and H bar. The unique distance that can be constructed is H bar squared over ME squared. This is otherwise the Bohr radius, and it's about 1/2 of an angstrom. The unique energy is ME squared over H bar squared, ME to the fourth over H bar squared, which is about 27 electron volts. This is twice the 13.6 ionization potential of hydrogen. The velocity is E squared over H bar. This is the same thing as alpha, the fine structure constant, times the speed of light. So it's C over 137. And this is essentially less than 1% the speed of light. And it shows you that the velocities that are characteristic of the electrons in this situation are essentially non-relativistic. There's also an angular velocity, omega 0, unique way of constructing that, mu to the fourth over H bar cubed. This is the angular velocity of the electron in the ground state of hydrogen. It's the same thing. So hydrogen, the hydrogen atom radius, Bohr radius, twice its ionization potential, it's a frequency of electron motion in the ground state. All these numbers are coming out as being characteristic of hydrogen. Why is it characteristic of hydrogen when we're trying to talk about a molecule? Well, the reason is that hydrogen has the same three fundamental constants that you have to play with. And so the dimensionless or the characteristic length, energy, time, frequency, and so on are basically the same. There are the same order of magnitude. That's why this works. So what this means, for example, in this potential is that the depth of the potential ought to be, if all things are working right, V0 ought to be comparable to K0. If you look at the actual numbers, you get 11.1 something or 11.0 electron volts versus 27 electron volts. And likewise, the R0 ought to be comparable to the Bohr radius. If you look at that, you get 1.1 angstroms as compared to about 0.5 angstroms. And what you can see is our order of magnitude estimates are off by roughly about a factor of 2, something like 2 to 2.5 is how far they're off, which given that you routinely throw away factors of pi and 1/2 and so on when you're doing order of magnitude estimates, this is not bad. This is working out pretty well. So although we don't have an explicit formula for this curve, we've got a handle on its various characteristic physical parameters, and that's where we'll pick up with this topic on next Tuesday's lecture. So that's all for tonight of the main lecture. Are there any questions about this?
This V of R doesn't include the central potential. I mean the
centrifugal potential. No, this is only the true. This is only the true potential, and as I explained, it's due to the overlap of the electron clouds.
Right.
The centrifugal potential, remember, physically is the angular part of the kinetic energy. So that's going to appear if you talk about this dumbbell rotating. But this V is just the V having to do with the distance between the two.
Okay. Yeah.
All right, good. Any other questions?
Can you go over the logic for why V0 here should be of the same order of magnitude as K0 for?
Yeah, because
C0?
because this curve, the dynamics of this curve has to do with the dynamics of those two electron clouds. And there are only 3 fundamental physical constants that appear in the dynamics of the electron clouds, EM and H bar. There's nothing else. And so the length that occurs, that comes out of it, like this minimum of the potential. Were you talking about the well depth? Is that
yeah, the energy.
The well depth is an energy. It has dimensions of energy. It's got to be of the same order of magnitude as the unique energy that can be constructed out of these constants. There's no other way.
Because there are 2 electron clouds that we're talking about here?
No, because the EM and H bar are the same parameters for both electron clouds.
Oh, okay.
Both electron clouds have the same fundamental physical parameters. By the way, the nuclear masses don't occur here. The electron clouds interact with one another because of electron cloud dynamics. That's nothing to do with the masses of the nuclei. So this potential is completely independent of the nuclear masses. You could question about whether the potential depends on the total numbers of electrons. There's 6 of them for carbon and 8 for oxygen. So do the numbers 6 and 8 occur in here? And part of the answer is yes, they do, but they don't have as much of an influence as you might think, because the electron clouds tend to interact by means of the valence electrons, which are the outer electron shells rather than the innermost ones. So that's the main reason for the very weak dependence on the nuclear charge. Those are good questions. Any further questions? By the way, to go back to that previous question, what I'm doing here is a classic example of dimensional analysis. You have a complicated problem, you don't want to solve it exactly, but you've got certain order of magnitudes, orders of magnitude that you can estimate, in this case on the basis of dimensional analysis alone. If there were further physical constants that appeared in here, for example, the proton mass or something, then you'd have further dimensionless constants that could be constructed, the ratio of the masses. And then you'd have a whole host of possible length scales. You'd have one length scale multiplied by m over m, and others as well. In fact, if I included the speed of light, which I rejected because it was non-relativistic, remember, where did I do that? Somewhere here I did that. I rejected the speed of light because the motion is non-relative. If you include the speed of light, you get a dimensionless constant, e squared over h bar c, which is the fine structure constant. And so in problems in which the electron motion is relativistic, you now have a whole host of length scales. You've got the Bohr radius, multiplied by alpha times alpha squared, divided by alpha squared, and so on. So you can take any individual physical problems and analyze, what scales of different spatial, time, energy, etc. scales apply to it. This is a particularly simple one because there are unique values for those various physical scales. Okay, any other questions? All right, if there's no more questions, I shall stop share screen. And I shall stop pause recording. One last chance for any additional questions. Okay, here we go.